So the area of the talk I'll be presenting today is on some work that I've been thinking about for a long time, and I think some of you have heard me speak about this before. I'm still very excited about it, in part because we haven't written anything on it, but there's a lot of exciting work going on, and it's been done with a series of undergraduate students that I've had in Greece over the past 10 years. So what I'll describe is a general framework inspired by information theoretic ideas and connecting with statistics for dealing with discrete time series. And I realize the title doesn't sound very exciting. Bayesian inference for discrete time series. It sounds like an awfully classical topic, and it is, but I hope I'll convince you during the talk that the framework that we've been setting up allows for very exciting and fun applications in many areas, including the fashionable buzzwords in learning and big data and so on. All right, so let's get started. The main problem with discrete time series is that they're hard to deal with, and there are a couple of reasons why they're hard. One is historical, because somehow most of statistics grew out of classical mathematics, and most of the methods we have are better suited to real valued data, where we can use ideas from calculus and even very old 17th and 18th century statistics. But also they're intrinsically hard, because there's no simple, universal, natural starting point like there is with Gaussian and linear models in statistics. And there are good underlying reasons why these are universal models in many types of data that we observe. The same thing is not true for discrete time series. And they show up all the time, and they show up increasingly often in modern applications. Part of the reason, or the main obvious reason, the first difficulty that one encounters is that in order to model dependence among discrete data, you need a lot of parameters. And that's why the starting point of a lot of our work in information theory is for memoryless sources. Once you allow series dependence of the type that we see in real data, in communications and in biology and so on, then you realize you need to estimate a lot of parameters before you can even get started. If you want to model a spike train, for example, a neural spike train from a primate's brain, if you look at it as a sequence of bits, where a 0 means nothing's happening and a 1 is a spike, then you know that there's very long-term structure in there, that structure is very delicate, that encodes information in very subtle ways, and you really want to be able to talk about the dependence in the time series, but that's very difficult because there are a lot of parameters involved. So you need a lot of data in order to deal with such problems. And because a lot of data until very recently was not available, a lot of ad hoc, very specialized methods were developed. And then the problem was that you had too much data, that these methods didn't scale well. So somehow in this business, you were faced with serious difficulties both ways, when you had few data samples and when you had a lot of data as well. And this was first, I think, observed and dealt with in the information theory world. Because in part, in information theory, unlike with statistics, we have operational problems where you know when you're doing well. So if you're doing statistics and I fit a model and Amos fits a model, it's not clear whose model is better, or Amos's model is generally better. Right? Or if someone has an estimate for a parameter, someone else has a different estimate, again, it's not clear who's right. But if you're doing compression, it's immediately clear who's right. And because of the fact that we had such clear operational goals, that gave us very rigid bearings for evaluating and developing methods. And a lot of what I'll talk about today is based on ideas that originated in the mid-'80s in the work of Rissanen, where he developed the idea of tree sources and finite state machine sources and so on. And then the subsequent work, about 10 years later, of Franz Willems and his co-authors on the context-free weighting algorithm. Now, I will ignore this history. I want to acknowledge that a lot of the ideas of what we did are based on Rissanen and Willems's work, but I will ignore that development so that I can tell a story purely in statistical terms, although you will be able to see the connection, and we're, of course, happy to acknowledge the influence. All right, so here's where we're going. I'll describe the general framework of setting up a statistical setting for dealing with discrete time series and describe algorithms and results and so on. There are a lot of applications that we've dealt with, and this list here is an honest one. These are applications that we've looked at. We've actually done work in all of these areas with real data, sometimes consulting with companies and so on. And we've had great positive feedback from people that are actually interested in doing applied work in these areas. I will not have time to discuss any of the funkier parts of this list, like content recognition and causality testing and so on, but I hope that by the end you will be convinced that we have a general enough set of tools that allows you in an orthodox way then to attack each of these problems. I'll just talk briefly about model selection, Markov order estimation, and entropy estimation, since these are the easiest applications to discuss without going into great lengths into the details. All right, so here's the basic setting. We will model our data as a Markov chain with a relatively long memory D, which means that the distribution of the next sample given the infinite past is just the distribution of the next sample given the most recent D symbols. D stands for depth because our models will be described by trees in a moment. And the problem, of course, is the curse of dimensionality, that the longer the memory, the exponentially larger the number of parameters that you need to describe your process. So if you have an alphabet of m letters and memory length D, you need m to the D conditional distributions to describe this Markov chain, and this is prohibitively fast growing. So the idea that was employed in the information theory world very early on was to use context trees. And the way these were used in information theory is slightly different to the way we will be discussing them today. In information theory, they were used just as intermediate steps and tools for developing good compression algorithms. We will think of these as actual statistical models. All right, so here's how this works. The idea is that if, let's say, you want to do prediction, in most data sets, you may have long memory, but this memory depends on what you've seen most recently. So sometimes you need to look very far back into the past. Sometimes you only need the very recent past in order to decide what your prediction is. And this, in homogeneity in memory, is described very effectively by a context tree. So what this means is, if you think of time as going in this direction, if I want to predict the next symbol, I just look into the tree and read back my previous symbol. So here's an example. Let's say most recently I've seen a 0, 2, 2, 1. So I go here and I see 0, 2, 2. I reach a leaf. When I reach a leaf, there's a distribution sitting at the leaf so that the probability of the next symbol, given that I've just seen this context, 0, 2, 2, I can ignore the 1 and everything that comes before it, is given by that distribution on the leaf. So here we have a fifth order Markov chain on an alphabet of size 3, which is described by 13 distributions. This is the number of the leaves on that tree, instead of the 3 to the 5 distributions that we would need if we describe it naively. So this is very nice. It's economical, it's fast, it's effective. And it's also cool because scientists like to understand a little bit of the structure of the data. And since we'll be taking a Bayesian point of view, I won't say that this is the structure of the data generating mechanism itself. I'll say that this is the amount of structure that the data tells us is present and that it's worth taking advantage of in order to do other stuff. So this is exactly how much structure there is in a data set, if that's the model that we fit, that's worth assuming we should be thinking about. And of course, it is of scientific interest to be able to visualize a model like this. All right, so how do you do that? Here's some just notation. Our models are trees. Our parameters are distributions on the leaves of the trees. I'll just write xij for blocks of data. And I'll often suppress the dependence on the first conditional context of the first D symbols to make the notation simpler. So if I have a model, if I have a tree, like the one we just saw, and I have my parameters, the distributions on the leaves, I can write down the probability of the data very easily. And you can do it in two ways, like we do with coin flips. I can just say it's the probability of heads times probability of tails times tails, tails, heads, and so on. Or I can just count and say it's p to the number of heads times 1 minus p to the number of tails. So here, this is done again in two ways. Either it's the product of the probabilities of each xi given its most recent past, Or I can say I'll look at every context in the tree and every possible symbol that could be following that context, and I will multiply the probabilities of seeing letter J following a context S raised to the number of times that I've seen this happen. Right? So it's just a different way of counting. Like we tell students that you can integrate this way or this way. Right? So the only reason I wrote this out carefully is because I wanted to define this quantity, AS of J, where for each context S, for each leaf of our tree, AS of J is the number of times that letter J follows this context S in our data. And this is how you describe the likelihood. Now, in order to do Bayesian statistics, we will need to define a prior structure on this problem. And here's how it goes. This is an ugly formula, but what it says is that there are a lot of models. If I even take binary data with depth 20, there's a gazillion models, and we'll see some numbers in a moment. But you want to be able to somehow make sure you don't always choose the largest possible model. You don't overfit the data. This is the main issue with model selection in this context. And the way we do that is by choosing a prior distribution that penalizes large models exponentially. So here's a parameter. There's a parameter of beta. You can just think of all this. You can think of beta and alpha as a half throughout. So this is basically 2 to the minus the size of the tree. This is more complicated because we have to make sure that it sums to 1. This is what this lemma says. That this is actually a probability distribution. There is some freedom in how much you penalize, how fast you penalize larger models by choosing this parameter beta, which is between 0 and 1. But for the purposes of this talk, you can just think of this as a half. So every time you add a branch of leaves to the tree, the probability goes down by a half, say. Right. So we have now a distribution on trees, and large trees or models, large models or a lot of structure, a lot of memory is exponentially less likely. And given the model, now we want to define a distribution of the parameters. So we want to define a distribution on the distributions on the leaves. And we assume that the distributions on the leaves are independent from leaf to leaf, and each leaf has a distribution which is the most sort of agnostic distribution, the Dirichlet 1/2. This is the Jeffreys prior. There are good reasons in statistics that explain why you may want to use this, although if we were being honest, Bayesians would say that you only use this if this really reflects your prior beliefs. But we're not going to go into the philosophical debate of all this. All right, so we have a prior on the models, a distribution on trees. Given a tree, we have a prior on parameters. And given the tree and the parameters, we have the likelihood. So we have everything we need to describe the problem. Now, the question is how you solve it. First of all, what does it mean to solve the problem? It means that you want to compute the posterior distribution. This is the goal of Bayesian inference. Bayesian inference doesn't give you point estimates. It doesn't give you yes-no answers. It gives you a distribution given your observations. If we were able to evaluate and estimate these in a very nice form, would be done for every statistical task that we might want to perform, from change point detection, model selection, or anything else you might want to do. And this is the starting point. This is the, what's it called, the diving board from which most statistics talks start. And they say, we can't compute this denominator. This is why Bayesian statistics for about 100 years was not used at all, because you realize this normalizing factor is impossible to compute in most interesting cases, in most cases that are not toy examples that we do in class. I don't even know that there's a name for this. In physics, it's called partition function. In this talk, we'll call it a mean marginal likelihood, because if you integrate out the parameters, you take the likelihood, you integrate out the parameters with respect to the prior, this part is called the marginal likelihood. And then if you average out overall models, we call it the mean marginal likelihood. There are other terminologies that are being used. So this is what you cannot compute in practice, always in statistics. And it turns out that in this case, this is something that you can compute exactly and effectively in linear time in the size of your data. So this is really the punchline of the talk, that in this really complex, interesting practical model, you can compute this exactly. You have it available, so this opens up a whole array of possible applications that one usually cannot perform in Bayesian statistics because you have to resort to MCMC, and for everything you need to do, you need a different type of approximation. All right, so how do we compute this mean marginal likelihood? First of all, let me tell you that this integral is very easy to do analytically. This is a very simple 18th century calculation. This integral, remember what this is, the likelihood, remember, is a product of powers of thetas. And then the prior distribution, which is a Dirichlet, is also a product of powers of thetas and square roots of thetas and 1 over square roots of thetas. So this turns out to be something very much like a gamma function that you can evaluate in terms of these things that look like factorials. So the marginal likelihood, the likelihood of the data given the model after integrating out the parameters, is just a product over all the leaves of your model of these p-estimated probabilities that can be expressed in this way in terms of the counts AS. Right? And then the question is, how do you go from this very simple thing to this very complicated thing? There are very many trees here. There's doubly exponentially many trees in the maximum depth that you consider. So this is a very large discrete space, and it's very unstructured. It's not like something that has some linear structure you can do your usual averaging or approximation over. It's a very unstructured space, but it turns out that because there are trees, you can compute this effectively. And the way you do it is by employing the context tree weighting algorithm. So the context tree weighting algorithm of Willems et al. From the mid-90s, from over 20 years ago, although it was used to derive bounds for estimating effective arithmetic codes for data compression, this is what it actually does. It computes this quantity, or it almost does that if you just slightly modify it. And this is how it does it. So let's take our data, have a long string of data, x1 through xn, and let's fix a memory length capital D. So we'll take every block of length d that appears in the data, and we'll create a tree that has these blocks as its leaves. And then, okay, so this is a big tree. It's not the tree that will fit to the data, but it's a big tree. We'll call this Tmax somewhere. Anyway, so this is your big tree. At each node of the tree, so each node, what's the node of the tree? It's a context of at most length d in the data. You count how many times you've seen each symbol in the data following that context. So you compute these estimated probabilities. There's no board, is there? It'd be easier to draw this. Okay, and then you take this tree and you start at the bottom and you average these probabilities going from the leaves to the root. And the way you do that is you go to each, well, at the leaves, you say, okay, my estimated probabilities are what I'll call now the weighted probabilities. But for each internal node, all the way up to the root, you average the value of the estimated probability where you are and the product of the weighted probabilities of the children of that node. So you do this averaging. This is like a dynamic programming thing. You do this averaging from the leaves to the root, and it turns out that what you get at the root is exactly this mean marginal likelihood. This is very exciting, and I'll show you in a minute why when we see some data. But for now, let me just say that this can be done sequentially. You can do it as you receive more and more data. You don't need to do it once and then stop. There's no question of training and then using, generalizing, or something like that, as people in learning like to say. It computes this doubly exponentially hard quantity in linear time in the data and quadratic time in the maximum depth that we allow. And as we'll show in a moment, this gives you a lot of freedom to do a lot of fun stuff. Before I show examples, let me show one more thing, which is if you take this algorithm and instead of doing averaging, you do maximizing. So if instead of comparing yourself to the product of your children, if instead of averaging, you just compare, and when you win, you prune the children. When the children win, you don't prune. You get a shorter tree, which turns out, this is the maximum posteriori probability tree algorithm, we call it. It does the same thing as before, except instead of averaging, it does maximizing and pruning. Then you get a tree, which is exactly the mode of the posterior model space. This is very exciting, and this is outrageously powerful, given what we're used to being able to do in Bayesian statistics. And again, this can be done sequentially in linear time. Okay, so let me now show some examples. Here we generated 10,000 samples from the Markov chain, the example that I showed in the beginning, from this fifth order Markov chain with alphabet size 3. And we took d equals 5, maximum depth equal 5, and equal 10. With d equals 5, you already have 10 to the 24 models. With d equals 10, you have, this is infinity in practice. Right? This is a finite number only in the mathematics department. And how do you select the best one of this many models? Well, we have a way to do it, and let's see how well we do. It turns out that with d equals 1, you get this model. With d equals 3, you get this model. And with any d above 5, within a fraction of a second on my 4-year-old laptop, you get, the exact model that generated the data. Well, this is very exciting that it can be so effective. So then one might get ambitious and we might start asking, okay, so now you've done some cool stuff. Maybe since you are able to get these, to fit these models, can you quantify how good these models are? It turns out you can. You can do a few things. One thing you can do is not just compute the mode of the posterior. Here we just computed the most likely model. The a posteriori most likely model according to the posterior distribution. You can compute a bunch of them because you want to know if the model you got has very high probability and everything else has very low probability, or if there's 1,000 models that are very different and about equally likely. So this is important to know. And it turns out that if you do this, I'm not going to parse this slide. I just wanted to show that there is an algorithm that can be outlined on a single slide. What this says is that if you do your bookkeeping carefully, you can compute not just the first, but the first few most likely models. And if you do this, there's a theorem that says that you do get the few most likely models, but if you ask for k models, the complexity increases dramatically. So you can get maybe 1, 2, 3, 5, sometimes 10 models, but no more than that. And then, because we have this marginal likelihood, you can compute very exact expressions for all the quantities of interest. So not only can I get the most likely model, but I can tell you exactly its posterior probability. I can compute the posterior odds between different models. And I can also, if you've done some Bayesian statistics, you can see where this is going. I can get the full conditional density of the parameters given the model and observations. This is what you need for metropolis sampling, if you wanted to do some metropolis type simulation for the posterior and model space. And this is the type of conditional distribution that you use in Gibbs sampling. And I'll mention these in a moment. But for now, let me show again on the previous example. This is with d equals 10 among 10 to the 5,900 models, give or take. We found the most likely one. Its prior distribution was 3.8 times 10 to the minus 6, whereas its posterior was 37%. So this is quite remarkable that this class of models is very well suited for some types of data. 10,000 samples is nothing for such a rich problem. And yet, you have very strong evidence, even with that small sample size, for the exact right model that generated the data. Then the second most likely model that you get is this one, slightly larger, and it's 6.29 times less likely a posteriori than the most likely tree. And then you get this third model, which is 8.82 times less likely. Right, so you do get these models. You get the first few that matter, but then, as we saw, the complexity increases very rapidly. You can compute the top 100, say, things in the posterior. And I should say that there's a couple of things that we won't see because I decided to just show results from one short, fun data set in a moment. We've looked at very large data sets up to the order of hundreds of millions of samples. One thing that we find is that these methods definitely don't overfit. So when you do find structure, structure is there. The other thing we find is that often the, the top of the posterior is quite flat. So you get a map model, you get an a posterior most likely model, but it's not unique. There's a bunch around it that may look similar, may look quite different, but they have similar probabilities. So then you want to explore the posterior a little bit more carefully. And the way you can do that is by doing actually MCMC. So going back to what we wanted to avoid in the beginning, we can use it now, but with much greater confidence because we know where we're going. We know the mod of the posterior. We can start from one of the top K trees and do a random walk on trees. So this is a Markov chain. The sample space is the state space of the Markov chain is the set of trees, the set of models up to some fixed D. And the way you go from tree to tree is either you add a full branch of M leaves or you remove one. So, and then you have these conditional probabilities that you can compute and you can do accept, reject using the usual Metropolis Hastings algorithm. And every time you have a tree, you can sample from the parameters of the tree exactly because you know the exact full conditional density. So I'll show now some examples of all of this on a single data set. So I have a sound file. By the way, this sound file is a recording from the song of a particular bird, the wood pewee. And when we started doing this, we started doing it for fun because it's nice to have something that is more tangible than just say stock prices or genetic data. You can listen to the song and so on. And then we found out that there's a lot of money in this business. For people that go bird watching or hunting and they want to have apps on their phones that create bird song so that they call birds and so on. But the main interest comes from the fact that we want to know what the birds are saying. Like most animal communication, like I guess most human communication is about sex, so these are mating calls. So the question is, what's the bird saying? Is it saying, come over here, let's have sex? Or is it saying, hi, my name is Peter, how are you, Julia, where are you from, and so on. So you want to know how much complexity there is. You want to know what type of song. Maybe I should mention this and tell you the answer in the end. So there are some, in the same species, there are some birds that have there's the Pavarotti of birds. It has a very complex song. And then there are some very boring singers that say la, 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 la. And there's a whole spectrum. So the question is, who do you think is more effective at getting mates? And I mean, in ornithology, this is an important question. Anyway, so this is the data we looked at. This is what it looks like in the time domain. These birds, the ornithologists tell us, have a very structured song, which means they have their whole song consists of patterns of 3 different syllables, 3 thongs. And I'll play a sound file while you look at this. This is the first 4 thongs, and this is, no, this doesn't work anymore. This is what they look like in the frequency domain. So these are the 3 different things. Now, let's see if this is going to work. If you can guess what's what. I think you get the idea. So we have this sequence, and we encode it as 0, 1, 2, these different thongs, and you look at the pattern, and you're trying to figure out if there's some structure of this IID uniform chirping, and we're just imagining the beauty of the bird song. So we had 1,300 samples, an alphabet of size 3, and we computed the first 5 models with depth equal to 20. And it turns out that the first model is this. And we found this both very surprising and very exciting because it shows that there's very definite structure in the song. There's very definite predictability in some cases and very much not so in others. In fact, the prior probability of this model is about 10 to the minus 5, and its posterior is 12.6%. So this was fun, and this is something that the ornithologists actually get excited about because they can think of this as telling them something about the syntactic structure of the birdsong language. And here are the top 4 trees. This is the most likely one. Oh, I'm sorry, this is the next 4 trees. This is the most likely one. We computed the top 5. It has a posterior probability of 12.6%. This has 2.2, 1.8, 1.8, 1.8. So these 5 trees have a total posterior probability of 20.2%. And you might ask, how do I explore more of the posterior? Already in this case, increasing k becomes hard, so we did some MCMC. We did 1 million iterations of sampling from the posterior. These graphs show you how sample averages of the frequencies of the first 3 models converge to you can see there's a straight line here. There's a horizontal line, which is the true posterior probability. And I just plotted these to show that we have a good indication that already with 100,000 MCMC samples, things seem to have converged quite well, at least for the first 3 models. These are the histograms of the depths of the models that we visit and the number of leaves of these models. So the model depths are is the more interesting part. You see that you have kind of an exponential distribution. So if you wanted to do Markov order estimation, and people do that a lot, here you could say, okay, well, my estimate is 1, 2, 3, 4. My estimate is that the Markov order of this bird song is 4. But it turns out that you can say much more. Not only that it's 4, but this is the posterior distribution of the model order. We can see exactly how much more likely your model is to have depth 4 than having depth 5, 6, and so on. So you get a very accurate picture, and you can do honestly Bayesian Markov order estimation. And a slightly more fun application is to do entropy estimation. But before we do that, I want to just show some results that show there's solidarity with theory, both in the information theoretic world, the way we're used to thinking about it, and in the statistics world. So this is sort of the result that bridges what in statistics is known as the BIC criterion. In information theory is called the MDL criterion. And it says that this model average likelihood that we get, this mean marginal likelihood, actually tracks the likelihood of every Markov chain simultaneously on every data string. So for every data string generated by any Markov chain with model T and parameters theta, the log likelihood that we compute is very close to the real log likelihood up to a penalty. Usually you want the likelihood to be large, right? And you can't make it large simultaneously for everyone, but it turns out that in a way you can. You can make it as close as the true likelihood uniformly for all true likelihoods up to this usual penalty where you have half log n. We think about this in bits because we think of these as code lengths if you put a minus sign here. So you pay half log n bits per parameter that you're estimating, or per parameter that's present in the true model. So since this is typically linear in n, this log n term is much smaller. So the first result connects with what we understand in information theory, and it says that this structure tracks all likelihoods well in this parametric framework. The second result is a much more standard statistical result, and it says that the posterior concentrates on the true model. So no matter what the true model is, if you see enough data, with probability 1, the posterior distribution becomes a delta function on the true model and the true parameters. And then if you really want to do estimation, you like to know that the posterior on the parameters is asymptotically normal. You can describe exactly what the limiting covariance matrix is, and the vector of parameters is indeed asymptotically normal. Now, there's a saying that says there's nothing less Bayesian than classical asymptotics in Bayesian methods, but it's nice to see that there's solidarity between the two. In other words, what we really care about is not this at all. We don't care about whether this is approximately Gaussian or not in the limit. We just care about the shape of the posterior, whatever that may be. But it's nice to know that there's solidarity with the classical theory. All right, so now let's do some estimation then. Let's try and estimate the entropy of this bird song, because we'd like to know how many bits is this bird telling its potential mates. And this is another thing that you may want to guess based on the recording that you just heard. How many bits do you think per second were there in that message? All right. So how would we do it? We would do the MCMC algorithm that we had. In other words, would create a Markov chain that samples from the posterior distribution on models, and then given each model on the parameters of the model. So given each time step, we have a sample from a model and associated parameters. If I have a model and associated parameters, I have a Markov chain, I can compute its entropy rate. Either directly, if d is small, I can find the top eigenvalue and compute the entropy rate. Or if d is large, this becomes numerically difficult and unstable. So what we do is we perform yet another Monte Carlo step. So in this MCMC, where you get a 3n parameters and 3n parameters, a 3n parameters, in each step, every time you have a 3n parameters, you generate 10,000 samples from that 3n parameters, actual fake data, and you estimate the entropy using the log likelihood. Oh, there's a log missing here. This is like a Shannon-Macmillan-Bryman type estimate of the entropy. So this is another Monte Carlo step in the process. So then, once you have this whole structure, you get your samples from the models, your parameters. Given the model and the parameters, you get samples from the entropy. Then you get all these samples. And what are these samples? These samples are samples from the posterior distribution on the entropy of the models given your data. So what do they look like? They look like this. So it is satisfying that they look quite a bit Gaussian. This is on the same Pee-wee data after 100,000 MCMC iterations. And this is what we got. This looks pretty close to a Gaussian. It's a little bit skewed to the left, I suppose. But you can fit a Gaussian pretty well. The mean of this histogram is 0.37. The median is 0.37 again. And it has a pretty small standard deviation. This is another repetition of the same experiment independently, another 100,000 samples. We get something very close. So we might quite reasonably conclude that there are about 0.372 bits per syllable in the song, or 0.217 bits per second. So it's 1 bit every 5 seconds. So not a very detailed story there. Even if all of it is meaning and none of it is noise, there's very little information that the birds are trying to communicate. So this sort of answers a quest that has been going on for a long time, especially in the neuroscience community, which had to do with the question of how to do honestly, truly Bayesian entropy estimation. And there have been a lot of attempts, and some of them have been more successful than others, but most of them do run into trouble. This allows you to actually do honest Bayesian estimation of the entropy from any discrete time series. And the last application I want to talk about is that of prediction. This is how you do prediction in a Bayesian setting. Again, the beauty of Bayesian theory in a way, or one positive aspect of it, is that for every task, there is an orthodox, proper way to perform it. Unlike classical or frequentist approaches, where for each problem you need to come up with a different ad hoc justification, even starting with maximum likelihood. In Bayesian theory, there is an optimal way to do anything. And typically, you can't do any of these anythings because you can't compute these posterior distributions exactly. So, for example, in prediction, there is an exact expression for how you should predict. This is the distribution you should be using for predicting the next symbol given the past. And it's the average of the likelihood over the posterior on model and parameters. And this posterior is typically not available. So people, what do? They do approximate model averaging. You try and find an approximation to the most likely models and their posterior distributions, and you try and average over these models and come up with some approximation to this thing via MCMC or other numerical techniques, like numerical integration and so on. in our case, we can do this exactly. We can compute this conditional distribution exactly because this is the ratio. If we forget this expansion that's typically used and just look at the definition of this conditional distribution, it's a distribution of everything that we've seen divided by the distribution of everything that we've seen except the next symbol. So these are two mean marginal likelihoods that we know how to compute in linear time. We know we can do this sequentially, and therefore we can do it for every new sample that arises. And one nice thing that happens here is that there's no separation between training and prediction. You don't just train and then take your predictor and use it. You update sequentially. And you know that in a strong sense, this is optimal. And indeed, we have found that, I mean, you can show that the computational cost is very reasonable. There is theory that already exists and applies to problems like this that shows that this distribution does converge to the true conditional distribution at the fastest possible rate to first order. So you have very fast convergence to the optimal Bayes predictor. And in fact, there's earlier work by Barron and others that shows that this predictor achieves the minimax Bayes risk in terms of log loss. So we know, theory tells us that this is, in a strong sense, optimal, and practice tells us that indeed it does very well. We've tried several data sets that people want to predict, and some of them quite important, including some work we did with some people in a mutual fund where, you know, prediction, slightly improvement in predictions immediately translates to dollars with a lot of zeros after the first digit. And we found that this method did much better than all other methods that have been used up to now on plain discrete time series. Now, this is the starting point of a very exciting development that I'm not going to talk about because this is ongoing work, which is the main limitation of this method. The main limitation of this method is that it breaks down with large alphabets. So if your alphabet is much bigger than 5 or 10, then you're not going to do well, and you know you will not be doing well. And the reason is that the class of models that we're considering become much less flexible with large sample sizes. The reason is that every time we add a branch, a branch to our model, we have to add m of them. Every time we add, I mean, these models have to be proper. It means that they have to cover all cases. So every time you add one new node, you have to add m new nodes. M is the alphabet size. So if every time you see some structure in one direction, if that costs you 10 or 20 times in terms of complexity, then the flexibility and the effectiveness of these models breaks down. And the way to move forward from there, or the way we've thought of that allows us to move forward from there, is to use these tree models as hidden states in an HMM. So you can do hidden Markov modeling, and that allows you to include, for example, real-valued covariates and do all sorts of other stuff that have been very effective both in genetics and in finance and stochastic volatility and so on. So now you have a process of hidden states that's much richer and also much more flexible. You can make it much richer just by creating a big state space, but again, you run into the problems of the curse of dimensionality and so on with the classical approach. So typically, people use very moderate alphabet sizes for the state spaces of these Markov chains. Having the tree structure gives you much flexibility, both in the memory and in the richness of the individual states, and allows for much more general alphabet sizes. And here's just a list, again, of the applications that I mentioned at the beginning and of actual data sets that we've been playing with. So I think I'll stop here and allow for questions on any of this.